Hello everybody, in this video I'm going to be going over something known as complex numbers. Complex numbers are numbers that include or have an imaginary part. However, if you really want to go technical with complex numbers, all real numbers are technically part of complex numbers, as you'll see in our definition of complex numbers. So what we define complex numbers to be are numbers of the form a plus bi, which a and b are real constants. So in this case, a can be 0 and b can be 0. So a number that's purely real, such as just a, is technically a complex number because you can write it as a plus 0i. You just do not see the 0 times I. Now, as we'll see with complex numbers, there's many interesting things you can do with them. However, we also need to know certain things about what I is. And of course, most of you already know what I is because you're watching this video. However, here's a brief introduction of I. I is defined as the square root of -1, as everybody basically knows, and I just stands for imaginary because the square root of -1 doesn't really exist in the real world. And what we'll see is if we take the powers of I to the 1 is equal to I squared is equal to -1, as we defined earlier, because the square root of -1 is just I cubed is -I, and I to the 4th power is 1. So that's pretty interesting. We can see that the powers of I repeat. Now, what about multiplying complex numbers? Well, this is basically the same as multiplying binomials using FOIL, the FOIL method, if you've heard of that. But literally what FOIL is just distribution. So you can just use the distribution property to multiply two complex numbers. Okay, here's an example of complex number multiplication. So I'm just going to use a simple method multiplying the first terms. So we have 2, multiplying these two, and then adding them together. We have 3i plus 4i. And lastly, multiplying the last terms together. So we have 6i squared. Now normally I would have these combined already and have simplified this I squared to -1. But just for the sake of this video, I'm going to make it a longer process. So adding these all up, we have 2 plus 7i minus 6, which goes to -4 plus 7i. So as you can see, multiplying a complex number by a complex number results in a complex number. So now we're going to move on to something known as the imaginary plane, or the complex plane. Now, what you use the complex plane for is just graphing points from one complex number. And we have two axes, the real axis and the imaginary axis. So let's take an example. Let's say we have 2 plus 3i. We'll graph this as 2, 3. So right here, since there's 3 i's and we have 2 real numbers. Now, in the complex world, there are different types of notations that you can use that are useful, extremely useful when you want to represent something. And they're also used in many formulas that are derived from complex numbers, so you may want to memorize these. The first one is the absolute value function, and it's basically just absolute value. Now, you may be thinking, how would you do absolute value on a complex number? Well, it's kind of different than what you've learned about absolute value before with integers and real numbers or whatever, where you just change it to positive. The definition is basically the same though. We know that absolute value measures the distance of a number, of any number, from 0. So once it finds that difference, that's just the absolute value. So when we're taking the absolute value of a number, say a plus bi, what we're doing is we're finding the distance from a plus bi to 0, which is here. So all we're doing is measuring the distance from a plus bi to the middle point in the complex plane. So we can calculate this and derive a formula from this. Using Pythagorean theorem, we have that the magnitude, which is what this is officially called, these two bars of a plus bi, is the square root of a squared plus b squared. So you don't want to say absolute value actually. You have to say magnitude because we just decided to make things like that. So now you have to say magnitude when you want to reference these two bar things, which is kind of annoying, but you'll get used to it. So we have that the distance between a complex number and 0 is a squared plus b squared, and the square root of a squared plus b squared, and that's also known as the magnitude of that complex number. We also have something known as conjugation. So let's say we have a complex number z, and we define z to be a plus bi. The conjugation of z, which you write in notation a bar above z, like what we have right here, the conjugated form of z is just a minus bi. And this is useful when you want to simplify the denominator or get rid of the complex number in the denominator. So we have a plus bi in the denominator, and most people don't like it when there's I in the denominator, so you want to simplify and move the I to the top. You multiply it by the conjugate of that number, which in this case is z. So by multiplying by the conjugate, you'll get something like a squared minus a minus bi over, since this is difference of squares, we have a squared plus b squared in this case, because we have technically negative of bi squared, and that simplifies to plus b squared. Now, one thing you may have noticed is that a complex number times its conjugate is actually the magnitude of the complex number squared. So we can actually simply prove this by just plugging in a plus bi for z. So we have a plus bi times a minus bi is a squared plus b squared. And in this case, it is true because of difference of squares. So this just becomes a squared plus b squared is equal to a squared plus b squared. Now, keep this in mind because it is pretty useful. Now, before we end this video, I have a quick sneak peek of what we're doing in a future video. And what this is just it's related to trigonometry, but you won't see it right now because all I'm doing right now is multiplying a complex number by I, and you'll see what happens. So we have z is equal to a plus bi, and we're going to multiply this by I, so this becomes negative b plus ai. And if you graph z and both z and zi, you'll find that zi is rotated 90 degrees counterclockwise of z. So that's just an interesting fact, if around the origin, of course. This is just an interesting fact that leads into what I'll be going to cover in the next video. So thanks for watching. I hope you enjoyed. Be sure to check out my other videos. Thanks for watching.